Okay, we want to discuss parallel polarization, and so I'll initially show this figure, which gives a nice three-dimensional perspective of what is meant by parallel polarization. So once again, here's our material interface where we would have material 1 to the left side of the z equals 0 plane and material 2 to the right side of the z equals 0 plane. The coordinate system is defined here, and so basically, in this particular example, you can see that the magnetic field actually points in the minus y direction for this figure. And so it's actually the magnetic field that is perpendicular to the plane of incidence. If you look, the electric field lies in the plane of incidence. So the vector for the electric field lies in the plane, which is defined as parallel polarization because we always define polarization with regard to the or with respect to the E vector. So since the E vector lies parallel to the plane of incidence, then this is referred to as parallel polarization. So let's look at what some of the equations for the incident, reflected, and transmitted fields would look like. So if we go to a picture that is two-dimensional, and in this case, x points in the up direction, y points toward us or out of the screen, and z indicates the z equals 0 plane indicates the boundary between medium 1 and medium 2. We're going to assume that this has zero conductivity, and later on we'll assume it is non-magnetic. So if we look at a vector that defines the incident E field, in this particular case, because H is pointing in the positive Y direction, in order for K cross E to give us H pointing out, E obviously has to be in this direction, in the direction shown. So if we take if we look at E, we can see that it's got a negative Z. If we break it into components, it's got a negative z component and a positive x component. And if this is sine of theta I and we draw a perpendicular here and we move sine of theta I and we move theta I here using a little geometry and trig, we find we can get an expression for the electric field that is its amplitude or modulus times x hat cosine theta I, which would be this component of that vector, minus z hat sine theta I, which would be this component of that vector. So it breaks into two components. Then in the exponent, we have e to the minus j beta 1, which is referred to as k1 in the Lobby textbook. Then the direction of propagation, you can see the primary difference. We still have z cosine theta in the positive, moving in the forward direction, which means it's got a negative in the exponent. We've got x sine theta in the positive x direction, meaning it has a negative in the exponent as well. So this is the direction of propagation. These are the two component distributions that act on the amplitude. Beta 1 is the wave number, or k in medium 1. So the magnetic field and electric field for incident are shown then here. Now the transmitted wave, basically the only thing that happens is instead of a theta incident, we have a theta transmitted. And so the vector directions all remain exactly the same. When we reflect, if you recall, what happens here is K has to reverse and the reflected angle is exactly equal to the incident angle. So because K reverses, then in order to maintain K cross E is equal to H, we have to have H then, and in order to meet the boundary conditions, the reflected H wave flips just as it did for normal incidence, and then the reflected E wave is shown here so that it makes the cross product consistent. So the expressions for the reflected E wave, basically the x hat cosine theta r is the same because in the x direction it's still pointing up. Now in the z direction it's pointing forward. Now if you think about it from the boundary conditions, remember that the tangential E has to be continuous, and so in order to maintain that we have to have that that component in the x direction to point in the same direction. So since k is reversed and the x component has to point in the same direction, E has to look like this and H has to flip. So the vector direction on the reflected H field has a negative sign on the y hat component. And then the reflected field, because it's traveling in the negative z direction, these two negative signs, this one and this one, multiply together to give a positive sign, which means you have travel in the negative direction. So these are the expressions given this coordinate system for E, H, and the direction of propagation or the wave propagation vector. So these can be basically just added to your formula list. All right, given the boundary conditions that tangential E has to be continuous and tangential H has to be continuous within a surface current, given that this is has zero conductivity and we have no surface current, applying those two boundary conditions, we can get the following expressions. So given these expressions for the parallel reflection coefficient and the parallel transmission coefficient, we can also, using boundary conditions, determine that 1 plus the reflection coefficient is the transmission coefficient times the cosine of theta transmitted over the cosine of theta incident. So please note this is different from the expression for perpendicular polarization. So as an example, let's just compare reflection for a couple of different cases. We have a light ray here that comes in with an incident angle of 40 degrees. It's obviously going to reflect. Some of it's going to transmit. And we're told that this is an air glass boundary glass having an index of refraction of 1.52. And we're asked to find the reflection and transmission coefficients for perpendicularly as well as parallel polarized light. So that means basically we have two different formulas for reflection and transmission. Both of those involve having to know the incident and the transmitted angle. So the first thing we have to do is we have to calculate what is the transmitted angle. So we use Snell's law, which is shown here, to determine the transmitted angle. And when we solve this, we get that theta transmitted is 25 degrees. So using theta transmitted of 25 degrees and knowing the index of refraction of the material, we can basically find the perpendicular reflection and transmission coefficients. So we have minus 0.285 for, after plugging everything in, for the perpendicular. We have 0.715 for the perpendicular transmitted. So these two expressions then give us a feeling for how much is reflected and how much is transmitted. And then for the parallel case, plugging into those formulas, we get similar numbers, and you can just see here that the main thing to note is that for the parallel case, particularly for the reflection coefficient, it's significantly smaller. It's less than half the reflection coefficient for the perpendicular case. So what this means is if we have perpendicular polarization, more of the wave is reflected than if we have parallel polarization. So you can actually extend that to say that if we have a circularly polarized wave, which is a linear superposition of perpendicular and parallel, if we have a circularly polarized wave, depending on the angle of incidence, the reflected wave will not be circularly polarized. It will most likely be elliptically polarized because the magnitude of the perpendicular component and the parallel component will no longer be equal in either the reflected or the transmitted wave. So that's kind of an interesting consequence of polarization at a boundary.